you go down the pad? I thought I'd mention we have a bunch of administrative things that are, yeah, okay. So the most obvious and pressing is that we actually have the midterm next class. And let me emphasize that it starts at 8:30. So please, please, please come at 8:30. Someone will come at 9, and I guess I don't know, we'll figure out some way to deal with that. I'm sure someone will come at 9, but just don't make it you or something like that. Okay, so just to review, I think all these things have been said, but just to review a little bit about the midterm. You can bring your Laplace transform table and a sheet of notes. So I don't know, you can choose what you put on it. I guess you can fit a whole lot on a sheet of notes. And I guess my theory is, in fact, that you won't look at the sheet of notes, but that the act of compiling that sheet of notes will actually be a great help. Same spirit as homework and things like that. So let me tell you what the coverage is. I don't think I've been too clear about that, but let me say exactly what it is. It's up through lecture 7. So it does not include the lecture we're looking at now. And it's also through the current homework, which is due today. So it's up through homework 4. All of that is fair game. Now, in fact, the material we're looking at now, lecture 8, if you look at it very carefully, you'll realize that it includes actually no new material. It's just, it gives names to things that we already knew about up through lecture 7, and it gives interpretations. So you might also say it includes up to lecture 8, but technically it's up through lecture 7. I guess you all saw that we posted on the web last year's midterm, which I think was a 2-hour midterm. I'm not sure. I think this time it's an hour and a half or something like that. So if you just wanted to gauge what does one of these things look like, just look on the web just to take a look at it. I think the other thing you'll find is that we snuck in all the problems. So you've actually done them all, right? So I think you'll figure that out, that we pulled them from last year's midterm and put them on current homework and things like that. Okay. Let's see. Oh, you might want to bring a calculator, because probably once or twice you're going to have to calculate b squared minus 4ac, where these are numbers. But I mean, it's to the point where what we really want to know is if you know what's going on, not what the numerical answer is. So you might want to bring a calculator. You're not going to be calculating anything more complicated than that, that's for sure. Okay. Are there any questions about the midterm, about how it's going to work and all that kind of stuff? So, I mean, I think if you're up on all the homework and the quizzes and things like, pretty confident on all that stuff, you're fine, I think. So, but we'll see. So there's a review session tonight. Again, all this stuff is announced on the web, which is really that's the real place where all the real information is, most up-to-date information. There's a review session tonight, which is 7 to 9 p.m. That's with, I guess, both Jessica and Leo will be there. They're going to be holding extra TA office hours. That's tomorrow from 3 to 5. And let's see. Oh, the other is homework 4 solutions, which are, I guess homework 4 is due today. That material is definitely covered. Definitely covered on the midterm. Okay, so it's important. And so we want to make the solutions for homework 4 available to you, and we'll do that basically immediately, like at 5 or something like that. Or we'll post it on the web tonight at 5:30 or something like that. So, or if you turn in your solutions earlier today, we could probably sneak. I mean, if you turn in your solutions, we can probably sneak you a copy of our solutions. The idea is, the main point there is it's going to be very important for you to have understood homework 4. So that was a hint, by the way. As far as I know, it's here. Yeah. I haven't checked whether we all fit. I don't know. We'll see. Because I think if our local SIDN people come in, I don't know. We'll see. It might be cozy. That's fine though. Doesn't bother me. Okay. Any more questions about this? That's all.
How many notes are we allowed to bring?
Yeah, just bring in a double-sided sheet or something like that, and I don't know. You can, I don't know. You can go to a copy place. You can do like the 8 per page thing, and then get a magnifying glass and stuff. But I think a single-sided sheet is about right. Sorry, a single sheet with 2 sides. Yeah, sorry. It's early, isn't it? Yeah, so I guess I don't have to tell you that. Yeah, so that's what it is. I mean, and you might, I don't know what you might put there. I mean, you might put on it things like the formula for the roots of a quadratic. I don't know why, but just in case, I don't know, you get here and it all goes, in a panic, it all goes out of your mind and you can't remember minus b plus minus squared b squared minus 4ac over 2a. I mean, it could happen, right? I don't. But I don't. Yeah, you can put that stuff there. Okay, or you can write down what the impedance of an inductor and a capacitor is, or up to you. Okay, maybe I guess the formula, the defining formula for Laplace transform, or maybe I don't know what you could write down on tricks for partial fraction expansion, but I don't know. I guess you could write some of those down. I don't really know what. In fact, I'll be curious to find out what you actually put on your what you figure out to put on your notes. Okay, enough on that. Let's continue with the topic of convolution. So as I said earlier, this material is not new. It's basically just discussing what we saw last lecture. I mean, what we saw last lecture in the context of circuits was that if you have a circuit with inductors and capacitors and op-amps and linear elements, and all of the initial conditions are 0, and you have a source somewhere in the circuit, like a voltage or current source that drives it, and then you have an output as a current or voltage somewhere else in the circuit, then the relation between the source and the other current or voltage, the input and output, is that of a convolution. Now, in the frequency domain, it's easier to say. I mean, you're just saying y equals hu, like that. Okay? In this lecture, we're going to concentrate on the time domain interpretation, which is convolution, which is, of course, much more complicated. But the idea is to get a feel for what on earth does this integral mean. It's worth understanding what it means because it comes up everywhere in all sorts of fields. Everything from economics, ecology, mechanics, dynamics, all sorts of things. This comes up. Okay. So here's one interpretation of it. I read this formula as meaning the following. It says that if t is sort of the current time, then y of t is the current output. It's what the output of the system is now. And this says that what the output of the system is now is an integral, which is kind of like a sum or a mixture. That's what an integral is. It's kind of a mixture of what the input was tau seconds ago, as tau ranges from 0 to t. So what u of t minus tau is literally what the input was tau seconds ago. If the current time is t, t minus tau is what it was tau seconds ago. So this says that a convolution is a mixture, in a convolution, the output is a mixture of what the input has been between the beginning of time and now. The weighting is given by this h. h of tau gives the weighting here. So for example, if h of tau is 1, this would describe an integrator, and it would say that for an integrator, what the current output is it's kind of a uniform mixture of what the output has been over the past t seconds, which is, of course, correct. That's exactly what an integral is. If h of tau, for example, rapidly falls off, suppose h of tau is large for tau near 0 and rapidly falls to 0, then what it says is that, by and large, y of t depends on what the input has been very recently. Everyone understand that? Okay. So, in other words, the rapidity with which h of tau falls off tells you something about how fast the memory in this system decays, because that's what it's saying. Now, you can also have the opposite. If h of tau grows with time, it says that the output here, right, h of tau could be e to the tau, for example. Then it says that the output of a system where h of tau grows with time is one where the weight, you put more weight on the remote past and less weight on the recent past. So this is one where you don't have fading memory, you have the opposite, where in fact events that took place a long time ago, their sort of importance and contribution to the current output actually grow with time, and in fact can end up overwhelming the recent memory. So there's all sorts of interesting things that can happen here. Let's see. Here's some examples. If you're looking at a plot of an impulse response, and you notice that, for example, h of 21 is very big, this has a meaning, and the meaning is simple. It says that the current output of that system depends very much on what the input was 21 seconds ago. That's what it means. Because in this integral here, if this is big when tau equals 21, it says that y of t has a very large contribution from u of t minus 21. Okay. Another example is if h of tau converges to 0 as tau goes to infinity, that says that the system has fading memory. It says that the influence of the output in the remote past is much smaller than the input from the recent past, and so on. So, there's a question?
Is that more common than the increasing memory one?
Well, it depends on the field, right? These are, yeah, you have to watch out about this because convolutions come up in zillions of fields. Now, it is true that in many fields, it's good to have a system that forgets its memory. In other systems, that's false. For example, in economic systems where y represents some economy, the goal is that y should expand, should grow as rapidly as possible, or something like that, right? So, but it is true that in most cases, what we want is something that forgets its memory. So there's lots of different versions of that. Yeah, it is probably more common in electrical engineering to study systems where you have fading memory. In other words, if h of tau, this impulse response, converges to 0, you say the system is stable or has fading memory. Now, if the transfer function h is rational, then that we can say exactly what it is, because we know when the inverse Laplace transform of a rational function fades to 0. And the answer is very simple. It's if all the poles have negative real part. So that's the idea. So all the poles have to be in the left half plane. Now, there's an extreme case of this, which you don't get with rational transfer functions, but you can have, and it's not uncommon. And it's this: if this impulse response not only converges to 0, but in fact actually goes to 0 at some finite time t and stays 0, in other words, it actually becomes 0, then in fact people would say that the system has finite memory, and that says that the input depends only on what the input has been over the last capital T seconds. Now, an example of that, if you look back at like homework 2 or something like that, would be something like a system whose output is simply the average of what the input has been in the last second. That's called an averaging system or an averaging filter or something like that. So that's, in fact, some people call that a moving average filter, because as t changes, you're taking an average over different things. And so that's used, by the way, to smooth out things like, one simple example would be stock prices are often shown on a moving average. But that's just a convolution. So now you know if you look at the paper and you see a dotted line below an actual stock price and it's smoothed out, it's a moving average. In fact, it's a convolution. Okay, another interpretation is a graphical one. And the idea is how to interpret this formula now in a graphical way. And here is the picture. The basic idea is this. The first thing you do is here's h, and here's the signal u, and we want to compute the convolution of these. Well, the first thing to do is to flip h backwards, so it looks like that. So you flip it around, looks like that. Now you imagine you grab one part of h, and what you're going to do is you grab the part that's at 0, and you're going to drag this along. Okay, so at this point I've dragged it to time t here. Okay, So what I have is a picture of h, but going backwards in time and shifted. Well, if you think about it, that is precisely what this means. In other words, h of t minus tau is the same as h. If I ask you to plot h of t minus tau as a function of tau, it is basically, it's a picture of h flipped backwards in time because it's minus tau, and then shifted by t seconds. So I flip this thing, and now I drag it. That's shifting by t. Now what I do is I take the point-wise product of these two signals, okay? And then I integrate, and I get the value. So for example, at this value of t, when I take the product of this dashed line and this black one here, what do I get? I get 0, and I integrate that, and I get 0. And that says that at least as t, for t between these two over this time interval, the convolution of this thing and this thing is 0. Everybody with me on that? Now, as I drag it, if I'm at this point, like that, the product of these is, in fact, this signal here. And I integrate that, and I get a number. Okay? Now, the other main thing is that as you keep dragging this, becomes wider and wider. And so, in fact, what you can see qualitatively is that as you drag t between here and here, what's going to happen is the amount you're integrating goes up linearly, like that. Okay? So this is the visual interpretation. Now, when you get to this point, and you take this product here, right? What you do is you get a function, you get something which has some positive area there and some negative area here. Okay? So as I continue to drag, the positive area here gets smaller because I'm catching less of it, and the negative area gets larger. And so it means that as I pull to the right, my total integral drops. It drops faster than it was increasing before, because I was increasing before only due to the fact that I was catching more of this positive part. Now I'm losing that, plus I'm also catching some negative part. So the slope goes down like this. And when this thing lines up like that, so that this little thing catches only this negative part, that's where the convolution achieves its negative minimum. Okay? And that's this value right here. Then as I keep pulling, I integrate less and less of the negative part, and I get this. So the important part, so this is a quick way to understand, how do you convolve this with this and to get this. And you should, I guess if I put numbers in here, the point is that you should actually be able to identify these. I mean, identify the slopes, identify this, and so on. Now, this result, we can also interpret or understand this result looking back at the previous interpretation. The previous interpretation, let me put some numbers on here. Let's call that 0.75 seconds right there. So if I just came up to you and I said, well, I have a system, and its impulse response is this function right here. It's 1 for 0.75 seconds, and it's 0. How would you describe in words what that system does? Just informally. Just describe it. What is the output at a given time? That's its impulse response. Just that. What does that system do? What is the output at a given time? Well, you just go back to this formula, wherever it was. I lost it. My first formula. Here it is. According to this, it says that the output is the integral over the last 0.75 seconds of the input signal. That's what it is. So at any given time, you simply integrate the last 0.75 seconds, and that's the output, right? So given that interpretation, we can also look at this signal and say, what happens when this is the input to that system? Well, up until this time, obviously the output is 0, because the average of 0.75 seconds of dead silence is 0, right? As time goes along here, I'm averaging the last 0.75 seconds of the signal, and it's rising. And I get my highest number about right here or something like that. Okay? It's also clear that once this thing has passed over here, like at this time, the output is again 0, because the average over the last 0.75 seconds is 0, right? Because the input has been silent for 0.75 seconds. Therefore, the average over the previous 0.75 seconds of the input is 0. Okay? So the other thing, of course, you can think of is when you think of a system which averages something over 0.75 seconds, your intuition should be that that has a smoothing effect. In other words, if you have a signal that's rapidly varying, and I compute sort of an average or an integral over 0.75 seconds of a running integral, a moving integral, if you think carefully about it, it should smooth it. Okay? And then you look at this and you look at that and you realize, hey, this is in fact a smoothed version of that. This thing kind of jumps up for a little while, then it jumps down less than it jumped up. The jumps are instantaneous here. Here's the output. It kind of does the same thing. It jumps up, then it jumps down less than it jumped up. But now it's sort of, it's piecewise linear. It's continuous, right? So it's been smoothed. Okay, so all of this is just all we're doing is interpreting this formula, nothing more. Okay.
Is that the equivalent of the original program we had?
Yes.
So the U and the T parameters?
Yeah, absolutely. This formula here, right? So where the t minus tau and the tau go, you can flip arbitrarily. These are the same formula. Well, they're not the same formula, but they're equal. They agree. The way you can show that is pretty easy. You simply introduce a new variable, like you introduce a new variable called tau prime equals t minus tau. If you change variable, you'll find that this becomes this and vice versa. So they're the same. Okay, so again, to review the graphical method, the idea is basically you flip the impulse response backwards in time, you drag it over t seconds, multiply pointwise by your input signal and integrate, and that gives you the output. So that's one way to explain this. Okay, so let's look at an example. This is actually a real example, and I think at this point you'll start seeing what the utility of all these things is. So let's suppose I have a communication channel. It could be like 1 mile of twisted pair wire. Okay, that's what it is. It's a telephone wire. Okay, now I put an input signal in at one end. I put a voltage, and I look at the voltage at the other end. Okay, this is given by a convolution. Okay, very, very accurately, it's given by a convolution. And suppose that the impulse response looks something like that. Okay, I just made this up. It doesn't matter. In fact, that's not at all unlike what a real impulse response would look like. T might here be in microseconds or something like that. Okay, but it doesn't matter. Now, the first thing to do is to look at that, and without writing down any formula of any kind, very important before you write down Laplace transforms, formulas, anything like that, is to look at this and get a rough idea of what does this thing do to a signal. And in this specific case, what we're talking about is when I put a signal, a voltage, on this wire at one end, what comes out the other end? Okay? Well, let's look at it. So basically, what is the memory of this? I mean, if I ask you, the voltage at the output of the wire depends on what input voltage is. I mean, does it depend on what the input voltage was 3 seconds ago? I'll go back to seconds. It doesn't really matter. It's probably microseconds, but no, it doesn't depend at all on it. In fact, one summary is to say, well, we don't know because I don't know what the plot is here, right? I mean, maybe it does depend on it, but in a very small way. So just casually, you'd say, well, I know this. The output voltage depends on what the input voltage has been over the last 2 seconds. By seconds, I just mean time units here. Okay? That's the first thing. Now, what if I asked you this? When I take an input signal and I make an abrupt change to it, or I do something violent to it, how long does that affect the output immediately? Suppose the input signal is 0 for a long time, and then all of a sudden I do something to the input signal. Like, for example, I'm transmitting a modem signal all of a sudden. What happens here? I mean, for example, for the first 250 milliseconds, what is the output of the channel? I'm not sure I would say 0, but I would say it's really small. In other words, that at one end of a channel, when you start messing with it, there's a delay. right? There's a delay. And in fact, the maximum effect occurs 1 second later, right? That's the fact that this has a peak at 1 second. So one very simple way to understand this, just very crudely, is to say that whatever waveform you put in at one end of the wire basically has no effect 2 seconds later. In other words, the wire has a memory of about 2 seconds. Okay? But the other thing is that effects do not happen instantaneously. In fact, the maximum effect occurs 1 second after it. So you'd roughly say it has a delay of about 1, and it smooths out signals on the order of 1 second or 1 time unit. Okay? So that's the picture there. And in fact, to justify that, if someone said, quick, approximate this as a delta function, what delta function would you approximate this by? First, you'd probably protest, which would be fine. You'd probably say, it doesn't look like a delta function to me. And you say, look, just quickly approximate this as a delta function. Where would you put the delta function? At what time? T equals 1. And its amplitude would be the area under this thing, right? Now, if an impulse response is a delta function at t equals 1, what is the system? It's a delay is what it is, because it says that the output is precisely what the input was 1 second ago. So again, these are just various ways to look at this and get a good intuitive feel for what it does. I guess if you can just look at integrals and formulas and understand this, that's great. So, okay, so we're going to do an example now, and here it is, just to show what the utility of this kind of stuff is. It's this. I'm going to put into this cable a simple 0.1 volt signaling system at 0.5 bits per second. Second means time units. Okay? So if this were actually microseconds, this would be at 500 kilobits per second. Okay? That's probably more realistic physically, but it doesn't make any difference. So here it is. It's a signal, and what it is for each time slot of 2 time units, it's either 0 or 1, depending on the signal, the Boolean signal that you're transmitting, right? So this is exactly like a very, very simple modem signal, okay? So here I'm transmitting the digital sequence, the Boolean sequence 0, 1, 0, 1, 1, and that's here. That's 0, 1, 0, 1, 1, okay? And I'm transmitting at 0.5 bits per time unit here, okay? So if this is the input, we calculate the convolution of this with this impulse response, which I would urge you to go back and figure out and make sure you believe this very carefully. But this is really here's actually the convolution. And sure enough, when you look at this signal and you look at this signal, that's the input and that's the output. And someone says to you, why does it look like that? You'd say, well, what do you mean? I mean, the cable has capacitance and inductance and so on. Not to mention, there's the speed of light issue here. And if you put a signal in at one end and the output changed instantaneously, we'd have a little bit of explaining to do. So you'd say, of course, the output doesn't come out looking perfectly like the input. I mean, it would if you had a 2-foot wire and the time scale was slow enough. So when you hook up something to an oscilloscope, your assumption there is it's perfect. But when it's 2 miles of wire, this is not the case. Okay? So then someone says, okay, what has happened to the signal? And you look at it and you say, it's been smoothed. But that's obvious, right? But the other thing you see here is it's been delayed about 1 second. So this should fit intuitively very well with you as the convolution of this and the impulse response, which is here. That's the idea. It should be no surprise. You should have an intuition. For example, if, let's say on a midterm or something like, no, I'm joking. On a final, there's a credible threat. On a final, if someone said that you got a bunch of data and 2 signals are here and one's the input and one's the output, there shouldn't be any question in your mind as to which it is, which is the input and which is the output. Right. Although, could this be the input of a system and that the output? What do you think? It actually could, but it sure is not a system with that impulse response. That's for sure. Right? You can have convolution systems that sharpen up signals, but they don't have an impulse response that looks like that. There's a question. No. Okay. Yeah.
Just for this particular example,
yeah.
can U really be the output of Y? It wouldn't be a causal system then, right? Meaning,
you have a good point there. No. Yeah. So let me explain his point. His question was, his question was this. He said, could this really be the output of a system with this thing? And the first thing you'd notice is in describing this as the output compared to that, the first thing you'd say about it is you'd say, well, it's been sharpened up considerably. Fine. And it's also been delayed -1 seconds. In other words, that whatever filter you have there is able to take a kind of a smooth signal and sharpen it up and actually predict it 1 second in the future. And this would cast, I guess, considerable doubt on it. So you're absolutely right. Right. Before, well, except for the following, right? You can have, well, we'll go into that later. That's a good point. Okay, there it is. Now the important, if you were doing communications engineering, the point here is that the output signal that comes out the other end of the wire does not look exactly like the input signal. But the point is it hasn't been messed up enough to destroy your ability to distinguish ones and zeros, right? I mean, so that's fine. So again, intuitively, and in later classes or whatever, you'll study this in far more in disgusting detail. The point is that this signaling scheme with this cable and this impulse response clearly is going to work. In other words, we can make a detector here that will tell you whether a 1 or 0 was transmitted. Okay? Now we ask the following question. Let's multiply this simple signaling rate to 4 by a factor of 8 to 4 bits per second. Okay? So here's our input signal. It looks like this. I'm transmitting some signal here. I guess 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. There it is. Now, the impulse response of the cable looks like that. Okay? Now, any way you want to do it, you can think about this. Any way you like it. You could do your flip and drag interpretation, or you can interpret what the convolution integral does. What you're seeing now is that what happens now is the output looks like that. Okay? This makes perfect sense because this system is kind of smearing together what happened at the input over a 2-second interval. But 2 seconds catches 8 bits of information. And you get this signal here. Nothing, there's not, in this signal, everything has been kind of smeared together. So for example, it's not at all easy to see this signal from this. Now, the truth is, by sophisticated signal processing, we can actually make a very good estimate of what the input was from this, right? But the point here is it's not simple like just asking whether the signal is above 1/2 or below. Is there a question?
If the impulse response was a delta function,
yes,
would we be able to reproduce the signal perfectly?
Absolutely. If it were a delta function, what would come out here would be simply this signal delayed by whatever that delay is, perfectly. The edges would not be ruined. It would simply be delayed. Then, of course, you'd be able to reconstruct the signal perfectly, right? Because it's just shifted in time. Yeah. Okay. So this is sort of the idea, and it gives you a rough idea. Now, this is called, by the way, just for fun, I'll tell you what this is called. When this occurs, this is called intersymbol interference. You don't need to know it, but you will later. It's called intersymbol interference, and I think it's it's clear what's going on here. It basically says that when you look at a certain output here, you're getting a contribution not just from the 1 or 0 that was transmitted then, but in fact, a whole bunch of other symbols. And in fact, it's very common when someone talks about ISI, which is intersymbol interference, for someone to ask, how bad is the ISI, or how long is the ISI? And what would you say about how much intersymbol interference do you have in this? I mean, when you look at an output here, how much interference do you get from how many other bits come in? Yeah, around 8, 7, whatever. So that would be the answer. So people would say, oh, the system I'm working on has, I don't know, about 7, 8 bits of ISI. And that's what people would say. And now you get a rough idea or feel for how this works. Okay? So this is true, for example, in all of communications works this way. Okay? All of things like magnetic recording, many systems work exactly this way. It's all convolution. And the idea there is convolutions kind of smear things up or whatever. At least when the impulse response looks like this. It looks like that. Okay? Okay, so that's the, any questions about that? 'Cause it's, again, we've done nothing new. We're just talking about a single integral formula and understanding what it means. So, okay, so first let me explain why this is called the impulse response. If you put in an input, which is a delta function, and you plug that into your convolution integral, what comes out is precisely the impulse response, which of course is why it's called the impulse response. The impulse response is the response to an impulse. And so what that says is if I have a convolution system or a transfer function here, and I put in an input signal which is like a delta function, then what comes out is the impulse response. Now, this leads to something called impulse response testing. In other words, one way to test a system is to take it, put in a very short acting and very large signal, and record the output. Now, if you can do that, you actually now have the ability to predict the input-output behavior of that box for any input signal. It's obvious from the formulas, but it's pretty, this is a pretty profound fact, right? It says that if you have a system, which of course you have to believe it's given by a transfer function, right? So, and let me give an example of where this is done. This is done in, for example, geophysics. In geophysics, impulse, how do you think you make an impulse in geophysics? So basically you're shaking the ground, and then you pick up the output with a geophone, which is basically a microphone or vibration detector, say a kilometer away. How do you think you make an impulse in geophysics? Huh? Yeah, high explosives. Yeah, so you drop in some high explosives. Yeah, that's what it is, right? That's your physical model, and in geophysics, the physical model, your intuitive model and reality, they're totally in agreement. You drop in some high explosive in the ground, you fire it off, and then you measure the geophone response signal. It doesn't look like that, by the way. It looks like this. There's a long delay. There's a delay. Then you get little things, bumps that look like that. And then actually you get multiple ones that look like that. And in fact, what these are is this is a signal. This is an acoustic signal transmitted down under the ground, hits some subsurface structure, and then bounces back off. And that's what these things are. And they look at the impulse response, and they can say all sorts of things about it. Like they can say, oh, that's the shear wave. That's a reflection off such and such a thing. Ooh, that might be a reflection off a salt dome or something like that. And so there might be worth drilling for oil. Okay, so impulse response is in fact plays a huge role in geophysics. Okay, that's really pretty much, except for maybe also in sonar. That's about the only area where people actually do true impulse response testing. Actually, mechanics, they also do a little bit of it, but usually not. And the reason is that when you put in a very large signal into a system, your assumption of linearity often fails, right? So that's why that's not done that often. But it's a very interesting fact that if you set off high explosives in the ground and measure the vibration at another place, a kilometer away. Once you do that, and someone says, yeah, but what if I had not set off a high explosive? What if in fact an earthquake with this, a displacement motion with this waveform had acted at that point and not a high explosive blast? What would the output have been? Okay? You can now compute it, and you compute it by convolution. Or if you like, by multiplying Laplace transforms. I mean, your choice, these are the same things. Okay? So this is not obvious stuff. Right, not at all obvious. Okay. Step response is also a very interesting idea. The impulse response is the kind of thing you want to look at if you want to get a rough idea of what does this thing do. Does it delay things? Does it sharpen up edges? Is the memory fading or not? Right? Does it this type of thing. You look at the impulse response. The step response is also used. This is as you would guess, of course, it's the output for a unit step input. And what that basically says is it says that the output is 1, the input is 1, and so your step response is the running integral of the impulse response. So they're very closely related, and in fact, one thing you'll need to do is to be able to translate back and forth between these two instantaneously, I mean, without even any hesitation. Of course, the running integral of the impulse response is just the running integral. So for example, the step response of this system here looks like what? What does the step response of that system look like? Well, it's the running integral of this, and so it looks, I'll draw it on another plot here. It looks like this. Well, what does it do? What's the running integral of this thing look like? Well, it goes up, right? It reaches its maximum slope right in the middle, like that. So something like that. Then it slows down again, and when it reaches 2 seconds, it's converged, and the integral increases no more, right? So the step response looks like that. That's the step response. And what I've just drawn for you is what the output of that wire looks like when you walk up to it and apply a step in voltage, right? And from the step response, again, you see things here. You see that that the delay is about, well, it depends how you define the delay. If you want to define the delay as the time it takes before the voltage gets to its kind of final level, it's about 2 seconds. If you want to define the delay as the time it takes for it to get halfway, the delay is about 1 second. Okay? You can also see that smoothing has occurred because you put in something with an abrupt transition in voltage. Okay? What came out is something that had a transition in voltage that went over a period of 2 seconds. Okay? Everybody see this? So this is it. Now conversely, if someone draws you a step response, you need to be able to differentiate that in your head, instantly, visually, and then talk about what that thing does. Okay? So here, there's a couple of oh, I should mention a few things. The first thing is we have a big-time symbol clash here, because S is the traditional variable used, dummy variable used to describe Laplace transforms. It's also, almost universally, the symbol used to denote the step response. So here, your parser just has to be pretty smart. If you see h of S, no one is going to think that S is the step response there. I mean, I guess it's the difference between human and and machine parsers. Okay, if you see S of t, right, and other hints are around there like here's the measured step response, no one is going to think that S here is the complex Laplace transform frequency variable. So, but just to warn you, this is the way it is. Now, step response testing, as opposed to impulse response testing, is widely used, very widely used. Huge numbers of industries use it. It's universally used in chemical process control. It's universally used. It's used in a lot of electronics uses it. Used in many, many fields. Mechanics it's used, and so on. So that's called step response testing. And of course, if you find the step response, you can differentiate and find the impulse response. And that's very interesting to think of what you're doing. So basically, if you have a box and you need to find its impulse response because you want to characterize that box so that you can actually do simulations and predict, you want to design a symbol that uses that box. That box might be, for example, a radio link in a communication system. Okay? Well, you know now that the only thing you need to know from that box is its impulse response. And you need to get either the transfer function as a rational function or the impulse response recorded in time. You're not allowed to apply an impulse to it because it's an RF link, and the maximum power output of your transmitters is, 5 watts. That's it. So if you ask it to put out 150 or 2,000 or 2 kilowatts, a little red light will come on and just say, sorry. At best. At worst, you'll ruin your amplifier. Your RF amplifier will be blown up and you'll be in trouble. Okay? So you cannot do impulse response testing. Instead, you do step response testing. And you find out what the maximum is, and then you step up halfway to the maximum, and you simply apply a voltage like that, or for example to a cable, and then you record the voltage at the other end. Now you differentiate what you observe, and that's the impulse response. So you see how you snuck around through the back door to get the impulse response, and the property you're using is very interesting. You're using the fact that convolution systems commute. That's what you're doing. In other words, let me show you precisely what it is that impulse response testing is doing. Here's a system that you want to test, right? That's H. What you're doing is the following. When you do step response testing, you really want to put an impulse here and get the impulse response there. Let me show you what you're doing in a block diagram when you do step response testing. You're applying an input, a delta function, but then you're applying that to an integrator. That gives you a step. Everybody with me on this? Okay. This gives you a step. This is the signal you actually apply. You never really form this delta function. That's sort of in your head. You apply, in reality, this step to this thing here. Then when it comes out, you differentiate the result. So here's this, and then here's the impulse response. You differentiate. Now, what is the transfer function of this thing? What's the transfer function of that? It's h. Yeah, that's it exactly. So in other words, you got away with it. You integrated the signal first, then you applied it to your device under test, then you differentiated it. And this triplet of convolution, these are all convolution operators. So this is like this horrible triple convolution. But sure enough, just by inspection looking here, an integrator followed by a convolution system followed by an integrator is in fact the same as that. Right? And so this is what allows you to do this. So that's sort of the idea behind step response testing. Okay, and that's very widely used. Many fields will show you the step response of a system. That's very common. For example, if someone shows you a power amplifier or something like that, they will show you a step response. For electromechanical systems, very common to show the step response. But even for all sorts of other strange things, like, for example, an industrial furnace, right, where you want to control the temperature, you'll see a step response will show you the change in temperature when you change the power input to the heater. You'll see a step response. Many other areas you'll see a step response. And just for fun, let's get a physical intuition for what a step response is in a suspension system, a vehicle suspension system. So the input is the road height, and the output is the height of the vehicle. What's the step response? In fact, what would be a really good word for the step response, or words in the case of a vehicle? Let's say a car suspension. What would you call it? Describe. What is a step response? What does it mean? Well, it means the road height is 0 up until t equals 0, and then it bumps up to 1. What's that sound like? It's a curb. Yeah. So in fact, yeah, it's what it is. So the step response has a very physical meaning there, and you might call it the curb response. Okay? And then everything makes sense. It tells you exactly what the vehicle height as a function of time is after you hit a curb, right? It won't go up instantaneously, right? But it'll start rising and then it'll wiggle and stuff like that. So that's the curb response. Okay. No, we have a couple minutes, so we're okay. So that's what the step response is there. That's the meaning of that. And it'll come up in lots of other areas, things like that. As you'll see, you'll get very used to describing the step response of something. Step response is also, although they don't use the word, step response is exceedingly important in all of digital circuit design. It's hugely important. In fact, in many ways, it drives the performance level and design of all of modern digital integrated circuits. The reason, let me just explain that. This is sort of just for just cultural, but interesting facts, right? Is that inside a processor, you have some gates, right? Here's a gate. And it goes to a long wire, and it drives some other gates, okay, over here. Now you have to remember all sorts of things, like this wire here, the distances are very small, right? If this were a millimeter apart, that would be a huge, vast, long wire in an integrated circuit, okay? Well, no, there's longer ones, but a millimeter would be a very healthy wire here, okay? Very long length. Okay. A very simple model of a driving gate is a voltage source that switches from 0 to the power supply. The power supply might be 1.8 volts, 2 volts, 3.3, 5 volts, right? It just pops up there, okay? A model for a wire, there's many that are used, but a very common one is just one that's a kind of a long list. It's a long string of resistors and capacitors. The capacitance is sort of the capacitance to the substrate, and the resistance is the resistance of the wire. Now, the resistance is small and the capacitance is small, but on the other hand, the timescales we're interested in are also really small, okay? So model of a driving gate is just another capacitance like that. In other words, you get a circuit that looks like that, and it has an impulse response. And the impulse response, I think you can even guess what it's going to look like. It kind of does nothing for a while, and then it kind of goes like that. That's a very typical impulse response. Okay? What does this impulse response mean for that digital circuit? What's it mean? What are the critical things here? What's critical here? The delay, right? That's the delay. That's a critical one. And just to see, I don't know if you get the idea here, if I made the wires really thick, so the resistances were really small, what do you think the delay would be? Small or big? Small, right? Big wires, RC is a rough time constant. This step response would look like this. If I made these wires little itty bitty tiny little things, right, then the delay might be very long. Now, of course, long delay, right, is measured in nanoseconds here, right? So what the step response of a wire in an integrated circuit does is it tells you the delay of that wire. Ultimately, that's exactly what limits how fast a digital circuit can work. Whether it can clock at 300 megahertz or 450 depends on the delays. For a whole bunch of the wires, doesn't make any difference at all. It's not critical. If it's delayed 8 nanoseconds, 15, doesn't make any difference at all. For some wires in an integrated circuit, known, of course, as the critical path, right? These are the wires that that limit the performance, okay? So that's it. So step response comes up throughout. It basically dominates much of the design at the transistor level of digital circuits. That's how it works. And the step response means everything. If this gate is set to flip when the threshold is a half, then you're looking for the point at which the step response reaches the critical value 1/2, because then the output would look like this, right? That's what a gate does. Okay? Okay. So this is just to give you another idea. The idea is to get a physical feel for what the impulse response, the step response is. The step response is the integral of the impulse response, but in many fields it has a very real meaning, and the interpretation is then critical. Okay, so we're done for now, over a little bit. Hey, we'll see you Friday, 8:30. Please, please, please come.